Welcome to the 9 a.m. talk on Faust in the classroom. My name is Julius Smith and I'm from CCRMA, and I want to talk about how I use Faust in my teaching. So I use it three ways primarily. The students are at the master's level typically, a few undergrads, a few PhDs, but mostly it's master's students, and they have some computer science background. Mostly they're there to learn about music technology, particularly signal processing. So the first use that's most commonly first seen by the students is the real-time audio signal processing demonstrations. So the idea there is to just introduce a topic by giving a demo and letting them hear it and operate the controls in real time. It's just to set the stage. This usually affects that they already know about, and we're just fixing ideas for the discussion. Then the second use is in live coding. So most of the live coding is in MATLAB, and it's a really great use of the flipped classroom where students have presumably read the assigned reading. They have looked at the video lectures from previous years that were recorded where I really went through all the material in great detail. And in this case, the classroom is really freed up to do whatever we want to do. And my discovery is that live coding seems to be one of the most engaging things that we do in terms of student participation and attention levels and so on. So Faust is a very nice live coding language because it's very high level, very compact, and it's very plausible. When you write it in a way that's very readable, then the students really get it, and it introduces them to Faust and gets them going in that direction, and good things come out of that. And then the final use is just a library of reference implementation. So it's a language in which one can implement the standard algorithms, the best known algorithms for various situations, and put them in a library that people can then easily access for their project work in the class, or maybe after they graduate when they're at some they have some assignment at work and they need to get something going. Very often that's in C++, and they can just compile from Faust to C++ and snip it out and put it wherever it goes. So it's a useful repository for best practices as far as we know. So since I believe I'm the first person to be talking about Faust according to the program today, I know Jan and Romain will be talking about it later. I will give you a first introduction. Faust is an acronym for Functional Audio Stream, and so that means it's a functional programming language that regards audio as a first-class object. Really, it's block diagrams that are first-class objects, and these block diagrams compute on streams of audio. So you can now also specify your graphical user interface, or GUI, and so the sliders and so on are very useful. So it's really wonderful for specifying a complete program that is usable right away when compiled and executed in some environment. And there are very many environments it can be compiled for. So it compiles to C++, but also to LLVM, JavaScript, even just plain C. And so it's a very nice set of back-end languages available. And then to get to the various platform environments, there's this notion of architecture files, which encapsulate the platform-specific API, the application programming interface. It is a way of so you basically write an example of the program that you want with little hooks that say where the the initialization goes, where the signal processing goes, and where the GUI elements need to be created and populated. And so you simply write the back end that the compiler finds the hooks for, and it's called the architecture file, and it really widens the immediate portability of everything. So let's take a look. I like to introduce it using the Faust Online compiler. And so here is what it looks like when you get there. You've got this very simple program, which is a one-character program, you might say. It's a function definition defining the function process to be plus. So process is a special function that's got to be there, and it is your main high-level function. So that's your main block diagram. And so it will then be defined typically in terms of other functions, and those functions are defined somewhere else. They can be before or after. Statement order can be arbitrary here. And when it all expands out, you've got a block diagram. And that block diagram specifies how the inputs are processed to form the outputs. So plus is a predefined special block diagram that means add two inputs to produce an output. And so one of the great features of Faust is the ability to generate a block diagram from the high-level language. And here is what we get for the plus block diagram. So process is plus, two inputs, one output. And I find that in working with Faust, I generally just have to look at this. In other words, I write the code, make sure the syntax is clean and that it compiles. And once it compiles, it tends to simply work. So if the block diagram looks right, it tends to work. So in other words, debugging is just looking at the diagram most of the time. So another thing I will do in class is show the compiled code. And so this is an example of what comes out if you've specified a particular application. It's better to start perhaps with none here. That's just my last example I had. So I'm asking for the C++ language, but I could also have these choices here. And I'm specifying the Linux platform, but I could also choose Windows, OS X, Raspberry, Android, ROS, and Web. And so under Linux, you see I've got quite a few choices here. And let's not get into them right at the moment, but there are a lot of standalone programs and a lot of plugin types. The ones I use most commonly are the Jack standalone programs. I prefer Qt, but you can also use the GNU Toolkit. Those are just alternative high-level Windows systems. And then for plugins, I like to use LV2. Thanks to Albert Graf, who I suspect is in the audience. Thank you very much for the LV2 support. And we also have the ability to generate plots for MATLAB, so you can inspect signals. We can go straight to Pure, also by Albert. And we also can go to PD plugins, Pure Data, and Super Collider plugins, and so-called chugins for Chuck, and so on, C-Sound even. So it's a very rich set of output possibilities. And so if you have OSC support in your architecture file, you can check it here, and then you can also generate an executable in the current chosen architecture. So let's look a little bit at this code. So this is the C++ generated from the Faust program, process equals plus. And here is some definitions at the beginning. So we get a class, and it's the DSP class. And you have the variables you need here, the sampling frequency that you're running at. This metadata is for all the various labels and paths to your GUIs, your graphical user interface elements. You can ask this class how many inputs does it have, how many outputs does it have. So it's 2 and 1 respectively. You can ask about sampling rates and so on. And now the real, well, there are initialization methods. You can initialize the instance, the or the class, so, and you can also build up the user interface. In this case, there's no user interface, so there's nothing going on in here. So here's the heart of it. It's the compute loop, and this is the heart of the signal processing, I should say. And so the arguments to the compute function are the buffer size, typically 64 samples, and that's your audio buffer size typically. And then you have an array of inputs and an array of outputs, and those are your input and output signals. And so our simple example has this inner loop. So it's a loop over all samples to just add the two inputs to produce the output. So this is your basic stereo to mono converter. And so it's very nice to get an orientation into how we're specifying low-level code in such a nice high-level form. Okay, that was an introduction to the Faust language and how we use it as an introduction to the language. And so now let's talk a little bit about the in-class demonstrations. So use these to introduce a topic and just establish the setting and generate motivation. Just talk about things that people generally know about. They know about most of these effects and spectrum analysis and so on. And so we demonstrate it and show them some live code for doing it. and then dive into how they work and how to build them in a bottom-up fashion. So the ones I use most often are the standalone QT applications generated directly from Faust using the architecture file Jack for QT and Jack for core audio. And so I'll typically start out with some of these demos on the first day to talk about all the various things we're going to learn. And then also whenever starting a new topic, it's good to do a demo for kicking it off, or at the end to see it in action. So the demos add practical utility and motivation to the class. Okay, here's a demonstration of the filter bank being used as a spectrum analyzer. So we have a constant Q spectrum analyzer made using a filter bank, and you see we have 20 bands spanning from a DC channel, low pass, 9 octaves below 16 kilohertz, and then a high pass final channel. And these are bar graphs that are configured in dB, and so they show the level of the signal that's there. Then down below at the bottom we have the averaging control, so I can average the spectrum and make it more stable, or I can let it change very rapidly, and this is just the filtering through time of the power output of the individual bands in the filter bank. And then this is just an arbitrary level display shift. And so this will generate a sine wave. So this is going to bring up the amplitude of the sine wave that's in the going into the input of the filter bank. And now I can move the frequency up and down. And so you see that even though it's a single pure tone, it excites primarily one of the filters, but it secondarily excites the other filters because it does have a roll-off associated with it. So the filter is not ideal. And so you always get these bands of energy in the spectrum, and you can control how much of that is there by the spacing and the order of the filter. So this is a basic spectrum analyzer made using a constant Q filter bank, which conforms to the nature of hearing. The nature of hearing is constant Q to a first approximation over most of the spectrum. The portamento control can be easily illustrated. If I crank up the portamento, then I get a slower transition in frequency. So it's very quick and easy to get the idea of portamento across. We'll leave it on pretty fast. So this is illustrating how to make a spectrum analyzer using a filter bank. And this is in a course on filters, and so it's a good way to set up a display and also talk about how you make that display out of filters. And this just gets the idea across initially. Amplitude down. Okay, here is the software listing for the demonstration of the sinusoidal oscillator going into a filter bank. And it's very short because it makes use of demos that are already defined in the oscillator and filter libraries distributed with Faust. So we have this process statement here, which is that the process function is defined as the oscillator library oscillator RS, which means R is for rotating phasor, S is the sinusoidal output. And so there's a demo already there for that. That gives us a little GUI for the amplitude and frequency, and we feed that to the spectral level demo in filter.lib. It's the nth octave spectral level demo, and it wants an argument bands per octave, which we've set to 2. More typical would be a third octave filter bank, but that was too big to fit on my screen, so I just changed it to a half octave filter bank, and it fit nicely. And then it has a mono output, which we feed to stereo for listening to it. So that's how simple the program is. Of course, when we get into the code, it'll be a few more lines, but not too many. It's a very compact, high-level language. Okay, this is a demonstration of driving a variable filter using a sawtooth oscillator, where we actually have 3 different variable filters. Down at the bottom we have a spectral level meter made out of a filter bank with power outputs measured and filtered for display as in the previous demonstration. We've got the same level averaging time control and overall offset control down here. So instead of a sine wave, we're going to drive this with a sawtooth. And so here's the amplitude control. So I can bring it up. So you see we have a broader spectrum here. I can wave the frequency around. Let's crank up the amplitude. Let's bypass the filter so we don't have that effect going on. So here's just the sawtooth. You hear the portamento control. Another common thing that's done in these kinds of oscillators, these are virtual analog oscillators, is detuning. So you have 3 oscillators, 1 right on the frequency you request, and then 2 that are detuned. These can give you the classic sounds of loosely tracking oscillators. So now, let's illustrate the filters. The sawtooth is chosen because it has a rich spectrum, and we can open the bandwidth up and close it down using these variable filters, whereas a sine wave would just get louder and softer if we filtered it in any way. So now let's look at the wah parameter. We'll kick in the wah. So that's the wah pedal that many guitar players have. This is actually a digitization of the Crybaby wah pedal. And so it's a classic staple in any guitar player's closet or garage or whatever he takes with him. So now let's go to the next one. Bypass the Crybaby and go to just a 4th order wah. Put up the amplitude and then open it up. So this is 4th order, so we'll look at the difference between 2nd order and 4th order filters. The 2nd order case is the Crybaby. It's only a single pole pair resonator. And then another very famous 4th order case is the Moog VCF. And so this is the one that synthesizer players mostly use. It's a 4th order Moog ladder circuit, very classic circuit, but we can implement it in the same way as this 4th order wah with 2 bike-wide sections. And there are actually 3 implementations here for comparison. So let's take a look. So that's more like a synthesizer where you've got a sawtooth and a voltage-controlled filter. VCF is a voltage-controlled filter. This used to be analog, controlled by voltages, and Moog developed the first classic circuit that's widely used. So I can bypass this and hear the original. I can implement it using biquads, and I can implement it using normalized ladder filters, and the difference there is whether or not it has artifacts when you rapidly transition it. And this is demonstrated in the Linux Audio Conference 2012 talk, so I won't belabor it here, but it's a very important feature of these normalized ladder filters that you can move the frequency instantaneously and not get a pop other than what it naturally has to do, in the sense that the energy is normalized in these filters. So the coefficient energy does not couple into the signal energy. You can arbitrarily modulate these filters even at audio rates without getting artifacts. Oh, and then I should illustrate another thing. This is another nice thing for the classroom, being able to illustrate what corner resonance means in one of these filters. And that is to bring up the amplitude and raise the resonance. So now it whistles. And down here you can see in the display what it means. When I raise the corner frequency, the resonance, you see more edge resonance at the edge of the low pass. Nominally it's a low pass filter, so you see here in the spectral display that the spectrum is low pass, and if I sweep it around, we also have nothing from DC to the fundamental. If I take the fundamental way down, I can fill that in. Get some very fat sounds out of these sawtooth, filtered sawtooth waveforms. Let's go for some corner resonance. Classic sounds. Here now is the listing of that previous demo of the sawtooth going into the crybaby and the fourth order wah, which is basically a fourth order low pass, and the Moog VCF, another fourth order low pass, and finally the spectral level demo. These are all in series, as shown by the colon operator there, and the output is panned out, or rather distributed out into stereo, and the grouping is ordered with these numbers in the strings. Okay, and these are all in the library. So this actually is an example distributed with the Faust distribution called VCF wah pedals.dsp. So that was a particularly easy one. And then the purpose is just to demonstrate the effects and get an idea of what they do. And then we dive into learning how to make them from scratch. This illustrates how I compiled those demos. I used the script Faust to Core Audio Qt that distributes with the Faust distribution, and I gave it the example that's in the examples directory, VCF wah pedals.dsp, and it created an application that I can then open using the open command, and that's how we got things going in the previous demos. Now I want to do something slightly different, which is to use Faust to jack Qt, and I want to compile the ZetaRev demo. And the reason I want to use jack is because I want to test it with a separate standalone application called the Reverb Tester. So let's look at that. Okay, this is an illustration of using two applications connected together through jack. So I have a stereo reverb tester, which just puts out an impulse in the middle or the left or the right channels. And you can also listen to the external microphones. You can also drive your system with pink noise if you want to hear that. And then what we're driving is the Zeta reverberator, ZetaRev 1. So it has an input delay, a low frequency, transition frequency. You can set the decay time, the time to decay 60 dB or T60 in 3 channels, or 2 lows, mids, and then there's a special high frequency channel that has a damping control. And then there's some equalization, dry-wet mix, overall level, and it's a very nice rich reverberator written in Faust. And so here's how we connect them up. We run Jack Pilot or some other Jack client, and you see that I've got the server running, so Jack is running, the Jack Audio Connection Kit. And so the routing button brings up this panel where I can connect things. So I can say, let's have the reverb tester drive ZetaRev. So I can double click on that, and it makes those two connections. It automatically connects any number of channels when you do that. So now we're ready to try it out. Let's give it an impulse. Okay, this is a classic example of the flipped classroom where I get into a place in a demo where something doesn't work, or I'm live coding and something doesn't work, and I appeal to the class, what's wrong? Why don't I get any sound? Why am I getting no sound out of this example? It really wakes them up. It really gets them engaged. They participate, they pay attention, they come up with ideas, and very soon, very quickly, somebody would say, you did not hook up the output. So I connected the reverb tester to ZetaRev 1, but I never connected ZetaRev 1 to the system. So let me do that now. Double click. So now ZetaRev 1 outputs go to playback 1 and 2. Reverb tester out go to ZetaRev in 0 and in 1. And that's all we need. So now we should get some sound. Very nice reverberator. Okay, so that was some examples of the standalone applications used in class. Now I would like to talk a little bit about the live coding activity. This is, I think, my #1 favorite activity for flipped classrooms nowadays. So the lectures are recorded, everything's written in the book, and when we get into class we're completely free to do whatever adds the most value. And I tend to measure that in terms of student engagement. So what really gets their attention? What gets them participating and really awake and galvanized for the class? Okay, this is a live coding example in Faust for the biquad. biquad meaning biquadratic transfer function. So it has a second order numerator, second order denominator, and so one of the great things about programming in Faust is that you can put the statements in any order, so you can make it look just how you want. So we can just say process equals biquad and fill things in. From there, you get to go in steps that you want. Now, how are we going to test this? I think we probably want to see its impulse response, so we can create an impulse by taking the constant 1 and subtracting the constant 1 delayed 1 sample. That'll give us a nice input impulse for the biquad. And so now we can define what the biquad is. So it's going to be an FIR part followed by an IIR part, and we can interchange them. One of the things we can show is that you can commute the FIR part and the IIR part and have the same filter. Linear time invariant systems are commutative. So that's the breakdown there. And then the FIR part is a moving average filter, second order. So one way to specify it, there are many ways to specify it. We could specify it as x. Well, we have a coefficient b0 times x, and then we'll have a coefficient b1 times x delayed 1 sample, and then one more for second order. So x delayed twice is that's the FIR part, or moving average part, and so we'll set those coefficients later. Now the IIR part is a little more tricky. So so this is feedback, right? So this is where I have to teach them a little bit about the Faust syntax and how it works. So we'll have a summer that takes an input signal and then feeds back through the feedback coefficients, and so now we get a delay from the feedback. So the feedback has already one delay in it, and so we can multiply by minus A1. That's just the sign convention to make it minus A1. And then for the other one, we want to have minus A2, but we're going to have to add another delay ourselves. So we'll have a mem feeding into minus A2 there. And now how do I create two signal paths there? Well, I have to take this feedback. I only want one delay here, and I want to then expand it out to 2 channels. And then one of them gets multiplied by minus A1, the other one gets delayed once and multiplied by minus A2. And then finally we add those together to get the feedback signal that then comes around to the input of the summer. And maybe that works. And so now let's define our filter coefficients. So the numerator coefficients, let's suppose we want a low-pass filter so that we want both of our zeros at half the sampling rate. So let's put in the polynomial for that. So that, oh wait, that would be 1, 2, 1. So 1 plus 2z inverse plus z to the minus 2 has 2 zeros at z equals minus 1. 2 zeros at z equals minus 1. And then for the poles, we normally have a polar representation, so we'll normally have A1 equal to minus 2 times r times cosine theta, where r is the pole radius and theta is the pole angle. A2 is also easily specified in terms of the pole radius, and so that's just a very typical definition. And then we can give the details of that. So r, the damping, is e to the minus bandwidth times the sampling period, e to the minus, and times pi. And to get pi defined, well, we could define it ourselves with arctan, but let's just go ahead and import music.lib, which defines pi for us. So that'll be defined now. So then we also have now theta, our angle, which is 2 times pi times the frequency we want times t. And so t is 1 over the sampling rate. And the sampling rate, let's just pick it to be 144/100. That's typical on my computer. And we need to pick a frequency and a bandwidth. So finally, we can get very specific and say we want our bandwidth to be, well, I don't know, let's say 100 hertz or so, and then we'll have the frequency be, let's put it right in the middle of the visible spectrum. So at fs over 4, we'll have a centered resonance there. But we call this a low-pass filter. We set the zeros to get a low-pass filter. So we have a pass band, and then we'll have a resonance at 1/4 the sample rate, and then it'll go down to 0 at high frequencies. So let's see where we are here. I also like to just show my workflow in Emacs. I feel like that's a good thing for the students to know about, and I'm just covering this down so it all fits on one page. And now I'm going to get a shell, and let's see if it compiles it all. So we first try to compile it. A miracle, it compiles. And now we will, let's look at the block diagram. I have a Faust to Firefox alias, F2FF, and so I say Faust to Firefox b.dsp, and there it is. So there is our constant, and then the constant delayed subtracted to form an impulse, 10000, and now we go into the biquad, and so what we name tends to be its own block diagram. Let's blow this up. So we have the biquad, and the biquad is defined as its FIR part flowing to its IIR part. The FIR part is the simple case of moving average. So the signal X comes in, the undelayed X gets multiplied by, that should be B0. B0 should be multiplying, let's see, that's just a name thing, isn't it? Oh, well, B0 and B2 are the same, so that's okay. They just happen to be bound to 1. So this is actually B0, and so X comes in, added to 2 times X delayed, and added to X twice delayed. All right, so that's the FIR part. Looks right, and it's good. Now the IIR part we're more worried about because it's got feedback. So here's our summer, and here's our feedback. There's our delay that we got from the feedback, and here's the straight through. Minus A1 is the coefficient. That comes into the summer just fine. And then minus A2 times the delayed feedback. The MEM gives us another delay, and that's our A2 coefficient, and that comes in the summer. And that looks fine. So when you look at this block diagram, you think, nah, it's got to work. All right, so let's see. So back to the command line. This is a shell within Emacs. So now I'm going to run Faust to octave on b.dsp. because I want to show you the really nice way of looking at things that are, filters. You can see them in the frequency domain. So now I can see what I've got here. I've got a Faust out. I can plot it, plot Faust out. That's the output. Actually, any number of signals. So if you had multiple output signals, they'll all be overlaid. And then here it is. So there's my impulse response. It's ringing like it should. That's good. And now I have a little alias called, plot the, it's a frequency domain view, and it gives me a log plot for, the default, and it also will give me a linear scale if I want to look at that. And so this allows us to look at it, and lo and behold, it is a low-pass filter that's got a pass band, 0 dB gain, plus something. It's a flat pass band. It's not normalized to 0 dB yet. And then we've got our resonance. Our 100 hertz bandwidth is kicking in here. And then we have our zeros at half the sampling rate. So it's qualitatively what we expect. And this is a more audio-oriented scale where you can see the pass band, the resonance at the corner, and then the roll-off, rapid roll-off. So that is a live coding example for a practical signal processing element called the biquad, configured as a low-pass filter. Now I can go quickly configure it as a high-pass filter by just moving these zeros from half the sampling rate down to DC. And we can configure it as a bandpass by just putting 1 0 at DC and 1 0 at half the sampling rate. And so those are the classic low-pass, bandpass, and high-pass outputs that you see in these, second-order cases. The state variable filter is an example of that. That's just another name for this kind of thing. So that is a live coding example complete with. Okay, so now we have the last third case, which is the reference implementation. So you've already seen some examples of input from the oscillator library, the filter library, the effects library, and I would refer you to the Linux Audio Conference paper for an overview of that. That's still on the web. You can download the talk and the video and so on. So all I'll say about it right now is that it's nice to have reference implementations in any field that make it very quick and easy to get things working, things that are already known. You don't want to really have to necessarily pull a paper and type it in yourself and debug it. You want just working code, right? So we should all be contributing to such efforts. So the fact that Faust compiles to C++, which is probably arguably the #1 language in the world these days, and ports immediately to a wide variety of host environments, like various types of plug-in and standalone applications, makes it an excellent choice. And it's also a very nice high-level language. It's very readable, and it's fun to write. Everything's really small and tight and elegant, and it generates very well-optimized code. I've been using it in app development and really have not been able to beat it, really. In other words, I've tried writing a few things in C++, but I keep coming back to Faust. It's just such a better representation, and the efficiency is really, really good. So it just keeps winning as the main language. And maybe I should show you a little bit of that. So I just want to conclude by saying that the experience to date indicates that the in-class demonstrations are useful to just sort of set the stage and let this class know what we're about to talk about, and it's fun, useful stuff. The live coding is an excellent class experience for flipped classrooms where the lectures are all pre-recorded, the book is all written, everything's there, and really you can do anything you want in the classroom. And we are open to anything in the class, but the live coding examples are the leading example of an activity that engages the class, gets them going, gets them contributing. I'm just really pleased with it. It's the most active and engaged classroom experience I've ever been able to generate. I'm not the world's greatest teacher. I tend to just kind of spew things in fire hose mode, but this is getting my classroom engaged in a way that is better than ever. So real-time demonstrations and live coding are really good uses of a flipped classroom in my experience. And then finally, the reference implementations are useful for practical development, and that's both for their project work that they're all doing, most of them are doing, and also after they graduate and are trying to do things in the world. It's just nice to have things they can start with, get things going. So I guess I'll close with a quick demo of this app that I'm working on. Okay, this is GeoShred. It is an app for the iPad that is based on a physical model. So in particular, you can get in here and configure the guitar. So this is a guitar implemented in Faust. It's got various string controls. It's got various body controls. You can even get some resonances and configure those in various ways. Then there are some nonlinear bridge features, another feature of the physical modeling approach, all implemented in Faust. And then in addition to the guitar, there are these effects, and these are also all written in Faust, so various distortion units digitized from classic schematics, the 4-octave equalizer, which is convenient, echo unit, simple delay line, chorus unit, and so on. There's quite a few effects. And so all this stuff runs just fine in real time, even on the iPad 2. I'm running the iPad 2 simulator here, and we're trying to keep it running on that. Okay, here's a performance by somebody who can actually play it. Sorry for the abrupt ending. Thank you very much.
All right, thank you a lot, Julius Smith, for your video. We have 5 minutes left for some questions. Like yesterday for Victor Lazarni, I would like you to come near the computer so that Julius could see you. Maybe there are some questions about what we've seen. Yes?
Hello Julius, it's Pierre. Thanks for the talk, very interesting. I was wondering whether you have any ideas about what the current limitations of the Faust language is. I mean, how do you see it moving forward? What type of features do you think are missing? Any ideas on this? Thanks.
Well, I'd love to defer that to Jan, who's sitting right there. I know. So.
You are embarrassed, right?
well, maybe we can split it into two pieces. I can say where I feel the need for more something, and you can say what the future is. How about that? We'll divide it up. The only time I feel like the language is not the most wonderful thing in the world is when I'm doing bidirectional connections, like in physical models sorts of things. Also, I made one error in my presentation. I said all of the effects were written in Faust. It's not completely true. There are some effects that are wave digital filters, which are fraught with bidirectional. In that case, it's a binary tree, but every connection in the binary tree is bidirectional. And so there's a theorem that every block diagram can be written in Faust. And I've gone through that theorem many times. It's a constructive proof that tells you how to do it. So you can just turn any circuit into a Faust block diagram. But it may not be the ideal representation at that time. It's general enough to do it, but it's no longer the perfect, high-level view. And so, so what some of us have worked on is a high-level scripting language that will take something like a net list, which is nice for circuits and such like that, and then compile that into Faust. So that then Faust becomes a lower-level language. So you can have a high-level script that really looks like how you want, and then compile that to Faust, and then down to C++, and then down to your machine. So, so there are good solutions for that, but that's the only example I have. So, Jan, what's in the future?
Well, I don't know how to solve the problem that you mentioned, and probably we should introduce some ideas of polarity into the so that still have the algebra of connections, but with polarities, and maybe that could solve the problem. But I'm not sure. And you don't mention another limitation, and I know that it's important for you, the fact that currently we are monorate, and it's not possible to do oversampling, but we are working on that, in particular with Pierre and his team. So the future is, in principle, that at least we will have the multi-rate stuff at the end of the project, the Fever project, that should be ending next 1 or 2 years, and on this problem, I'm really interested in any ideas that you can have. How would you like, if you have an example of how would you like to specify things by bidirectional things, then it's probably very interesting to see how we can do that. I don't think that once we have the right way to specify things, the implementation should not be a problem. Just to find should we extend the algebra? Should we just introduce this idea of polarity? I don't know.
Yes, I didn't mention the multi-rate aspects because I'm very focused on models right now, but absolutely once we have the multi-rate capabilities and the ability to turn serial signals into vectors through time, I'm very much looking forward to spectral modeling applications and getting FFT kinds of processing going. So yeah, I'm very much looking forward to that.
peux poser une question?
Yes, yes, you can.
I have one question: is how the students how they combine the MATLAB and Faust? How do you split things, basically?
Well, I don't really combine them. So
Okay.
the MATLAB is its own world, and we do things in MATLAB. It's usually analysis. We're usually just like when I did Faust to Octave. That's the most tightly coupled we are. I use Octave instead of MATLAB, but on campus we use MATLAB, and so you know, MATLAB is your analytical engine, your visualization engine. It's just for taking in signals, forming spectra, and plotting them, viewing them, turning them around. So it's an analytical tool, whereas Faust is your implementation tool for really making a system. So it's on the generative side as opposed to the analytical side, and so we use both, but there are really two ends of the two sides of the coin. And I normally do most things in MATLAB, and then it's for an alternative representation that can be used for implementation in a very convenient and ready to go way. That I introduced Faust. So in other words, they've already seen a lot of MATLAB, and they've seen a lot of spectra, they've seen a lot of analytical points of view, they've seen plots of impulse responses, and they've seen block diagrams written in the conventional way. And so the Faust view is kind of the icing on the cake. It's an alternative representation, and it's ready to go. That's the big thing. It's ready to run with as a real-time plugin, and that's what really gets them going.
Okay, we're gonna try to keep a tight schedule. I'm sorry, but it's going pretty fast. So thank you a lot, Julius Smith, for your presentation.